Our pleasure to welcome Athénaïs Gautier, who will give us a talk with a long back.
So thank you, David. So as I said earlier before the mishaps, I will be presenting some things that I've been working on during the PhD that has to do with learning distributions away from strong distribution hypothesis and with a non-parametric method. So the main reason we are doing that was that one of the questions behind the PhD was to solve stochastic inverse problems. So being able not only to go from parameter to outcome and to response, but go the other way around. And that tends to be quite complicated to solve these kind of problems. And if you are able to have a good model of your situation, if you are able to say that you have a perfect modelization, then it's much easier to make inference. And that's what we are aiming at. And because of that, so we have a kind of challenge that is given to us by the application we wanted to tackle. So we knew that we would have a setting with costly model evaluations. So a few simulations, we knew that we would have data sets with heterogeneously scattered data. So some region of space would have a lot of data points, some other a few. We knew that would have sparse data points, so few or no replicates. And that we wanted to have a model that would be able to lift inference in this setting with some application in natural sciences. So I just showed you for reference some kind of data we would like to be able to model, but this is actually the setting where we had a lot of data points and we would like to be able to say things before getting to this regime where we have made a lot of costly evaluations. And so because this was a motivating question, we had all of our challenges set up before us, and we just needed to find the right way to address it. So the main challenge can be reformulated as being able to estimate a probability distribution that varies across space. And the space, the index will always be denoted by x in this presentation. So every time you see an x, it's an index. And every time you see a t, it's the response you want to model. So that it should be a bit easier to follow a bit what is what. And so, for instance, here you have the red curve that are the true distribution you would like to be able to model. And you can see that it varies widely in shape depending on where you are in space. You also see that you have different data observation. So maybe you have a lot at x1, just a few at x2, none at all at x3. And you would like, in this setting, to be able to learn to have some uncertainty quantification on your prediction, because you surely should be more confident on your prediction around x1, for instance, than around x2 or x3. And how to address this setting, how to do something for this regression task that is not so easy to tackle because of its heterogeneity. So what I'm going to do is I will use some test case or red thread data sets that is quite easy to follow. That is coming from the Boston housing data set that tends to be well known in regression tasks, because it's actually a 1D example, 1D in response, 1D in index, that displays a lot of the behavior we would like to be able to address in natural sciences. So for instance, of this, we have a data set that is taking some statistical summary of properties, housing in some neighborhood. And you have the proportion of old houses that are more than 80 years old in the neighborhood. And you also have the median value in tens of thousands of dollars in the area. And so in the data set, you see that when you have more old houses, you get lower value because it tends to be an older neighborhood, except for a small survival bias where you have some really high value or luxury properties that lift the cost up. And therefore, you have this kind of bias here, survival bias here. But you see that when you have a lower proportion of houses, then you have some kind of bimodality with two small clusters. So it's something that we would like to be able to see and to model. And it has these kind of features of evolving, having a change in skewness, having a change in modalities and all that. It's easy to follow, so I'm going to use that to show the implementation first. If you were to pull the data in arbitrary bins, which we don't want to do because we don't want to have to make choices for the inference, well, you would see these kind of histograms also showing the changes in shape, skewness, modalities, and all that. But what we want to do is a model that does not require you to pull in arbitrary bins. And you can see that even if we were to do that, it will still be not so easy to deal with the uncertainty because some bins have like 14 data points and some have more than 100. So it would not be accurate to be treating these bins in the same way because they don't have the same weight, or they're not informing you as much. Not all bins are as informative as the others. So this dataset has all the things we would like to be able to tackle. It has also no replicates, I think, or just a few ones, like a few hundreds of points. And for a given x, you only have one output t. And it's easy to do visualization, and it's quite intuitive now that you have the feeling of why the houses are costly or not. So what we are going to do is introduce the model that is the spatial logistic Gaussian process for this density field estimation. Study a bit its mathematical properties to understand why it's likely to work or not, and then discuss a bit the implementation and show application. And if I have enough time, I will also show you one inverse problem that we tackled with it. So the building brick to make the spatial logistic Gaussian process is actually something that was used just for density estimation. So forget about the index, you want to learn the density. There was this model called logistic Gaussian process that leverages a Gaussian process on just the output t. So it's like a random function with Gaussian process. And then if you take it, you exponentiate it to make it positive. You renormalize it with respect to the response. You have a random function that is positive, that integrates to 1. So it's like a random PDF in flavor. Cannot formally say that, but that's the idea. You're building this prior random function that look like PDFs. And so if you look at this for density estimation, if you take draws of the GP, transform them, you get the colored curves. If you take the average, you get the black curve. And so it has a lot of flexibility. You can have the mode a bit everywhere. You can tune the kernel and landscape hyperparameters to get more flexibility or less flexibility, etc. And then if you get some data, for instance, this histogram, or the data underlying this histogram, you could condition it on that, and it gives you estimation of the underlying cluster layer. So you can use that in density regression. And I just need to check if the reference is compiled. So I will update, if I upload the slides, I will upload the one with the references, but I think it did not compile properly for this one. So it's been around for more than 40 years. It was studied in 78 for the first time, this LGP. It was introduced in 78, and then it's been studied until most recently. It was around 2008 or 2010 with some papers from Van der Waart and Togda studying properties, posterior consistency, and this kind of properties. So what is nice about the logistic Gaussian process is that it's intuitive of why it's implying some prior of the function we want to model, and it admits a real natural extension to a spatial setting, because you just have to add your x, your index. Now you have a GP that is a random function of x and t, or a random function of t indexed by x. And this random function, you can also transform it. You can make it positive. You can renormalize it with respect to the response only, so only the t. You have asymmetrical rules. And then you get something that looks like a random PDF, or random feed of PDFs. And so that's what we're going to use as prior, and that's what we are going to condition data to be able to make our model. So I'm trying to be a bit cautious of what I call a random PDF, because it's not so easy to speak about the measurability structure of PDFs. But actually, it's still the flavor and still what is behind it. So the first thing I want to know is whether this prior is suitable to model what I want to model, because I showed you histograms of barrier per space. I was like, oh, I want to have viability, I want to have expressiveness. How do I do that? So first, I'm going to introduce you to this plot. What I did is that I took 3 realizations of my GP. I transformed it by exponentiating it and renormalizing. And I plotted the PDFs across slices. So every vertical line has the corresponding PDFs or the corresponding X. And so you can see a bit how it evolves in shape. For instance, for the first panel, the first realization, yeah?
Is there guidelines? It is the same guidelines for the choice of the kernel in logistic Gaussian process and Gaussian process, or are there some differences?
There are some differences, and I will touch upon something that is quite important in this a bit later in the slides.
Okay.
If that's fine. But you still have some underlying principle that's behind your kernel that if you want to learn from your neighbors, you should have a kernel that is suitable. So just what I want to show is that here I took some Mattern 5.5 kernel, and you see that, for instance, here I get quite peaked around small values of my response for the I-hex, but in the middle I get more bimodal. I see with the second realization that I can model this kind of higher peaks around the tail. So that's something I wanted to have because I had these high value properties for high values of x and high value. So I have this kind of shape. I can change shape depending on where I'm in the model. I evolve smoothly, and it seems to be suitable for what I want to do because realization have different shape that I would aspire to reproduce. So with this, I can go beyond distributional assumption in quite a flexible way. So before I show you how to use it in practice, I will just show you a few ideas of why it works and what we understood about this object, mathematically speaking. So we have this object that I said, oh, it's kind of a random field of densities, but how to formally speak of the SLGP? Can I say, oh, it's a random field of densities, or is it ill-defined to speak of random densities? So how to tackle the math behind it? And it turns out that it's not really easy to speak about the sigma algebra of densities, but something that is quite well defined are random probability measures. And so what you can say is that instead of saying that the SLGP is a random density, you can say that it's the representer of a random field of measures by just adding an integral at the numerator, and then random, so all my references broke, but this is a reference on random measures. Random measures are quite well defined with a nice measurability structure, and so the representers, it's quite visual that this is a representer of random Nicodim derivative of this, and then everything is set for us. We can easily speak of what is happening. And then I can be a bit more informal by saying, yeah, since it's a representer of the Radon-Nicodim derivative, and I will mostly be in continuous setting, I will speak of densities because I have this underlying work. And another thing that is quite important that we understood during our work is that what is characterizing the SLGP is not directly GP with transform, but its increments. And the reason for that is quite simple, actually. So I will take that board for 2 minutes. If you look at the, no, it's a bit too high. I wanted to have the slide still. If you look at the SLGP, you have exponential of z of x t renormalized. And that you can just easily write it as the ratio of exponential, 1 over the exponential of z of x u minus z of x t du. And so just by looking at this, you understand that what is actually driving the behavior of SLGP.
Very
Yeah.
sorry. Can you just yeah, it's difficult to read.
Sorry.
Yes, it's really perfect.
Okay. That's mostly what I wanted to show. So you just rewrite it simply by putting everything on the denominator. And from this, it appears quite visually that it's actually going to be driven by this kind of increments of at the same x but different t's. That's going to be driving the behavior. Another way to see it is that I could easily add another term that only depends on x on numerator and denominator, and it will cancel out anyway. So if you want to understand what's happening in SLGP, if you want to study it, what you should focus on is not directly the GP transform, it's its increments at the same x. So that's something that we understood, is that you just want to have increments at the same x and different t, and that's why you're going to drive everything, the distribution, the properties, and all that. So we understood a bit of that, and so we were wondering, well, I want to learn to do distributional learning with no replicates. So if for one x I only have one response, then I need to be able to use some spatial regularity of some sort to also use the neighbors to inform myself, because otherwise I'm doomed. Or I would just put some directs everywhere and then I would not be much happier. And so because of this, we started studying the regularity of the SLGP. And so we know that for Gaussian processes, the regularity can be informed by its variance, it can be informed by its kernel. And we're like, oh, for SLGP, we should look at this object's kernel.
Yeah, it is the reason why there is an influence of the choice of the kernel is hidden there.
It's hidden there, yeah. So for instance, the choices of the kernel, you have a wide family of kernels. If you just look at increments like this, that would just cancel out. So, yeah. So we had a look at few results to understand how smooth it is across space. Is that if I assume that my SLGP, my SLGP, or the underlying GP, because this is just the increments of z of xt prime. If I assume it's regular in the sense that it has some Hölder condition, then I get two results. The first one is that if I take my SLGP, it will be almost surely continuous with respect to some dissimilarities defined for PDFs or for distributions. So if I take, I took a family of 4 dissimilarities, what I get is that for these dissimilarities, almost surely when I take a realization of the SLGP, if I take this realization at x and at x prime, they will be Hölder continuous for this. And another result we had is that we not only have the almost sure continuity, but we also have rates for the expected power similarity. So we have a second result that is if I take, for instance, my SLGP, still in random form at x and x prime, I take its distance or dissimilarity, so for instance, the Hellinger distance. I can put a power of my choice plus take the expectation of that. Then I'm able to bound this continuity rate. Yeah.
In your definition of the different, the integration is with respect to Lebesgue measure? Or
Yeah,
like
it's with respect.
Not F2? So it's not like analog of Tolbert-Kleibler variant. It just that's what we use. I know.
No, it's with respect to Lebesgue. Yeah. That's because this is actually inspired by what's done in Gaussian processes to have the spatial regularity. You look at the canonical semi-distance.
I meant for that distance V at the very bottom of F1, F2.
This one, so to be fully honest, it's because I took a lemma that was from a paper by van der Waart, and they were also stating the rates for this V.
I think it's the integration is sort of log squared, but like F2 of something du, I think. Because it's like a variance of the Kullback-Leibler.
But I also have Kullback-Leibler, it's not the same.
Yeah, anyway.
Sorry, so I took the V that was in the paper, and they were using this V already. So maybe I made a typo, but...
Yeah, I was just curious if it was a different object. Sorry.
I think it's because it was called a squared log ratio. So I guess if it were Kullback-Leibler variant, they would have called it that.
Okay.
So yeah, no. It's not a typo, it's just something different. Okay. So we have this continuity rate saying that depending on how sensitive the dissimilarity measure is, you can just bound how it will behave. And we found these results by using Gaussian measure theory, like and some tools like Fennick theorem, and also some standard results from spatial statistics like Dudley's theorem. And we wanted to check if the bounds were tight, because during the derivation, we were quite careful to handle the constants and everything. So we just wanted to check that we were right. So we did some simulation. We simulated this left-hand term by doing unconditional simulation of SLGPs and computing everything with just Monte Carlo approximation. And we just checked the right-hand bounds compared to this. And we tried a few power, we tried a few kernels that had different spatial regularities. And what we found is that we were careful enough with our bounds because the empirical rates we have with simulation and the theoretical ones just align perfectly for our simulation. So with that, we were happy. Another result that we have that is inspired by another paper that should be cited here is that you have some posterior consistency. So if you have enough data and your model is well specified, like if your model is obtained by transforming a function that is in the support of the GP, then you will be able to achieve posterior consistency, so we will be able to recover branches. So we have the two ingredients we needed. We have some spatial regularity that we understand, so we'll be able to draw some things from the neighbors, and we know that if we do that, we will be able, in the Bayesian setting, to recover the branch. So it's reassuring enough to be going to the implementation, how to do it in practice, and what makes it work, and what choices we need to do. So you have these amazing references. You have two papers of people that have studied something quite similar to the SLGP we use, but in a different setting. And you have a paper we've published on with the results plus my PhD thesis that will be available for, like you can see, yeah? Yeah, from the results, we took it as compact. Yeah. because so first it was not too bad for our application because we had the similarities that were bounded to some extent, and so we wanted to model things that were positive and not above a certain threshold. So we took compact, and it also made all the results much easier to derive. So what we want to do is to be able to condition on data, because right now I've been speaking about prior, I've been telling you, oh, I will do Bayesian at some point, and that we have Fourier consistency. How do I deal with actual data? So I will assume I have a set of n observations. I have my locations where the experiment was performed. I have the output of the experiment that I assume are some kind of realization of independent random variables whose distribution depend on where we are in space. And what we can write is the likelihood of the observations, because thanks to the independence assumption, it will just be the product of SLGP evaluated at the places that we are interested in. So we have this product of n ratios with integrals at the denominator. And because of that, it's not so easy, because now we have this right-hand term that is not so easy to tackle, because you have this infinite dimensional object that is the GP that is transformed in a nonlinear fashion. You have this integral that has the GP over the whole response space T. And how do you handle that for likelihood-based computation? It's quite cumbersome. It's a bit hard. So because it was a bit hard, we decided to not do it and instead use finite rank Gaussian processes. So instead of taking a full Gaussian process with everything infinite dimensional, we take only combinations of deterministic basis functions weighted with normal weights. And that's what's called finite rank Gaussian processes. So it's still a Gaussian process. We can understand what's the kernel behind it. Everything is well. But now everything is much easier if you want to do the likelihood-based computations, and you can write a posterior without having to worry about whether you're allowed or not to write this kind of Bayes theorem. So in this setting, the posterior, the normal weights, they would have a posterior proportional to their normal multivariate normal prior times this product of ratios of, this is the exponential of GP, and this is the integral of the exponential of the GP. So it's a,
yeah. I have another question. How do you evaluate posteriorly your models, and also your confidence intervals and so on?
So you mean like the performances, or it's called the performance and all that?
Performances and performances also in terms of uncertainty quantification.
Yeah.
How do you do that? Is it difficult? Is it a challenging problem?
Yeah, it's a bit difficult, because what you are trying to compare is a sample, so data points, then realization of, and then random densities.
Yeah, true.
So there are some principled approach. So what I'm going to show in the presentation is mostly visual, like, oh, we're happy because we have some uncertainty, and we're happy because the shape changes.
Yeah.
But you can also do scoring, actually. So you can use the whole literature of probabilistic forecasting, and then the scoring applies, and then you're comparing samples with distribution. It's what it's made for. So thankfully, there is a way to try to do it in a principled way. It's still something we're exploring, actually, but we know how we plan to do it.
Okay.
Yeah. So we have a posterior, but something that is extremely nice about this n-dimensional posterior is that you can derive its gradient, Hessian, and everything with respect to the weight epsilon, the subject of interest that we have, and it's log concave in epsilon. And that's actually extremely nice for 3 reasons. The first one is that if we want to optimize it and to find its mode, it's going to be fast, because we can just do gradient-based computations. We will be optimize it. It becomes a convex optimization problem. We're happy. We can do maximum posteriori for extremely cheap compared to what the problem is. And so it means that we are enabled to take a lot of basis functions. We lost a bit of flexibility when we said we will take finite rank Gaussian processes instead of full Gaussian processes. But actually, we can take so many basis functions that it does not matter that much. The second thing that is good with this log concave is that once you have found your mode, you can do Laplace approximation. It will give you some approximation that is quite fast. It's direct byproduct of the optimization, so it's quite easy to have. And we have an idea, because of its log concave property, of how good this approximation is. And then if you just want to do the full Bayesian inference, you can do Markov chain Monte Carlo sampling, and it's going to be relatively fast because once again, you will not have any problems with your chain mixing, with all these things, because it's log concave. So everything will be relatively fast, relatively well behaved. We are quite happy with this, which is also a bit of the reason why we took this formulation, and also why when we said, oh, we make it positive and then renormalize, we could have used any other function rather than exponential. But with the exponential, we have log concavity.
Okay, so what you are saying, you don't need any mixing property of your chain because you.
Well, you have it because it comes from the log concave. Like,
okay, thank you very
it will be really easy to get it because
okay.
you don't have multiple nodes where you might.
Yeah, for sure.
Yeah, you just easy. You know, everything is leading to the right place because it's a global property. It's log concave everywhere, not just. So that's going to be really well behaved for the estimation and for all the practical aspects. And so we have this. We still have some choices to make, actually. The first one is that how do I select my basis function to be expressed? Sorry, did you have, yeah? So in 2 slides, we will be speaking about it. So the first choice we have is how do I select my basis function? Well, at first we're like, oh, we can take anything that is expressive enough.
Can you learn it as a dictionary learning, for example?
So you know that in some paper that were not displayed, they did some process of some life and death process to select the function to keep and all that. But I think that because of the normalizing constant, it's a bit easier to just take basis function, pre-evaluate them, and use them later. I think you could learn it, but I'm not sure it's necessary, especially since everything is a bit fast, so you can allow yourself to take a bit too much, and then more scale, they don't really matter. So we tried taking, for instance, L2 basis of polynomials to try to do this, and as it turns out, it's not the best choices. Like, not all functions are good for that because of the numerical stability. Because you still pass everything for an exponential, so sometimes it can be a bit too wiggly. So here, if I take an increasing number of basis functions and I take Legendre polynomial, I would have some realization of GPs that are not something I would wish to see in my learning problem. So what we've explored a bit empirically which basis functions were nice and which were not. And what we found is that you have 2 types of families that are well behaved and numerically stable. Is taking some multivariate Fourier types, so sines and cosines, inspired, for instance, by random Fourier features, but you can also take other frequencies. Or you can take something inspired by inducing points, so like in the variational setting. I tend to prefer the Fourier type basis because the inducing points, you still have the issue of you want to have weights that are standardized. So you need to have this covariance matrix between the inducing points that you take the square root of. And that is not always really nice when you increase the number of points, while you can freely increase the size of the Fourier basis. So I prefer Fourier basis personally because I think it's more stable, it's easier to get it working. So we took these kind of functions. If you find another family you like that is numerically stable, that does not have this kind of behavior, you can of course put it in the estimation. Then what we did for the normalizing constant is that we just said we'll take a naive quadrature. First, because we observed that it was not changing too much, not so sensitive to number of points, so it was fairly reasonable to take quadrature. And also because then you can pre-evaluate your basis function that we're going to use. You can store it at the beginning of your evaluation, and then you just have to plug new values of epsilon. So it was making also the computation faster and more efficient. So we are going to use just quadrature, and we are not taking any fancy quadrature. A bit because at first I was a bit too lazy to do it, and then because I realized that if you formalize it like this, you can also tackle discrete probabilities. So you can, because this is just, instead of the integral, it's just the integral with respect to the counting measure, basically. So you could say, oh, I don't want to have the whole integral, I just want to model integers, and then this is going to work. So I just kept it like this because I saw it as a byproduct of the discrete.
But it would be interesting to take into account design of experiment, because, for example, we have some, or to combine it with
I don't think for the integrals, because they really have a rule for every x. So I don't think we should spend more time. At some point, I was also thinking, and we explored a bit, like you also have some Laplace for exponential family. Sometimes you can do Laplace if the term inside is big enough. But then you need to find the modes of each element in the integral, so it's not really interesting. Also, you want to avoid having too sharp, so you don't want to have too big values inside the exponential. And I think because it's in the likelihood term, you cannot afford to give more weight to point, because otherwise you're artificially going to inflate the likelihood around places where you have many points. So I think for me it was more satisfying, at least intuitively speaking, to treat every integral the same way, to not be able inflating the influence of some or underrating the same. It's not the best integral you can have, but at least it's treating everyone in the same way. Maybe there are some clever schemes to do. So you have some references, of course. So in this, I put references, I put my thesis, and I put a lot of vignettes where actually I have implemented in R package. I submitted to Prime, but it's not out yet, but I have a lot of vignettes of showing how to use the package through an estimation and showing it on application cases, and showing also how I got most of the images that I use later in the talk. So when I make the slides available with the references that compile nicely, you will have these links and these vignettes and these references. So for now, I want to show you a bit how it behaves on my test case, and then I think I will have a bit of time for the thing I want to talk about. So first, good news, it works. So here I run just the maximum posteriori estimation, because it's just easier to plot. I only have 1 point estimate, so I can just plot my curves. I don't have to deal with the uncertainty and the probabilistic prediction. So if I have this, so at each x, the vertical line starts, and I can have the corresponding PDF that is vertical, and I have behind it the scatter plot that was used to train. So I'm happy about it, visually speaking at least, because I tended to have values that was dropping when the age, the proportion of old houses increased, and I see that the mode of my distribution tends also to follow this trend. I was saying, oh, here I have some kind of bimodality where I can see that I'm more skewed here, so I'm putting more emphasis on the fact that I have data here. I can see that I've put a bit of probability mass around the high values here, which was also something I wanted to have to be able to model this. So I was able to represent what I wanted to see in my data, which means that it seems like the data incorporation have worked for this. I used a heuristic for the length scale for this one, because I also wanted to do some exploration work on the impact of these things, but just it's already satisfying. What I can also do is say, oh, I will take the slice that is here, I will beam a bit the data around it to have a histogram. Oh, yes?
In Matrix 5/2 kernel,
yeah.
It's isotropic in X editing.
So
Tensor, right?
No, it's anisotropic. Like you can just, instead of taking the isotropic distance between your all vectors, you can just put some weighting in the.
Yeah, it's not a tensor.
No, it's not a tensor. It's.
So it means in T and X.
Yeah. Well, I think it makes sense at least. Yeah, but yeah. So one thing that is important is that you want to have some mixing, because otherwise you kind of tend to be able to distinguish some elements that are part of X and part of T, and you have product. And I tend to think that if you want to leverage everything, you would like to have the mixed and not the product. I have to think more carefully about it, but it works. And in the end, what we do actually is that we use some random Fourier approximation of this. So you have actually functions that you have some cosines of W transpose the concatenation of xt and sines of the same thing. And the frequency is sampled according to the spectral density. So if you were to, I don't know how it would behave numerically speaking. If you have, like in 2D, it's okay. If you have just one dimension for x and one for t, it will be okay. But if you have a larger dimension for x, I don't know how it would behave to have products of this instead of.
No, I like to
Yeah.
You want to be global. I see them in the spectral density of omega.
Oh, wait. So it works, this is the max. So I can, yeah, I was about to say you can just take, let's say, one slice, you can put a small bandwidth around it to just have a look at the binned histogram, also to check that it's indeed following the histogram. And that's what we did. And if you take a bandwidth of 5 around something and you look at histogram, you can really see that it's following the data. And so you can have evolved. The skewness evolving, the modalities evolving. So it's satisfying, visually speaking, on this application. But now I'm showing you just the maximum posterior estimate, and I was telling you I wanted to have some uncertainty quantification. So you can also run the Markov chain Monte Carlo, and then you will have not only one point estimator, you'll have a probabilistic prediction. And so here, I can do the same binning of histogram. So all the black curves are one posterior draw, so one output of the MCMC. And the red curve is the average, the posterior mean. And the reason I'm plotting it like this and not, for instance, like we do with Gaussian process regression with these sausages, is that for me, it does not really make sense to use like notion of variance because density is quite structured an object. It needs to integrate to one. And so I think I tend to lose information when I look at just this summary of these bands around it. But you can still see that here you have a lot of variability with functions moving a lot. When you have few data points, when you're closer to a place where you have a lot of data points, everything is a bit more concentrated and behaving the same closer to the average. So we have some uncertainty that evolves depending on how much information we have. Since we are learning the full distribution, we are learning also byproducts really easily. We can just, like this, get something like the moments and their uncertainty. So I can have the expectation depending on where I am. I can have the standard deviation. That is not true. And then we can also have the skewness, and it's something that we observe. We're saying, oh, it's broader when you're close to small values of x, and more biked when it becomes closer to this, and you can see it in the skewness. So that's one functional you can get really for free once you have done the estimation. One that is more interesting, and to me it was more impressive to see it for the first time, you can get quantiles. You can get any quantile you want, and it's going to be really nice in the sense that here I'm showing you the SLGP, the quantiles with estimated with SLGP with the plane traits with the ribbon around it. And just to compare that it was making sense, I also ran some quantile regression with the dashed line to see that it was following more or less the value I would get with standard method. And in the area where I don't have a lot of data, you can see that the quantile regression crosses because it's not consistent, while because the one from the SLGP comes from distribution directly, it cannot cross. By design, it's impossible for it to cross. And overall, it's behaved more or less like it should. It seems to be more certain of the prediction for most quantiles when you have more data, more uncertain when you have fewer data. And you have some discrepancies between the quantile regression and the SLGP, but then if you look at the empirical distribution of data, they are like, the quantile regression is a bit off on the side actually. So it's not, a sanity check, it's good enough. But I was really happy to see this kind of visualization for the first time. I was really impressed. I was really happy with myself. No, I really find this kind of plot is cool. So now we see that it behaves well in a data set that we understand well. I think, yeah, I will try to speak a bit about inversion and stochastic inverse problems that we worked on during the PhD. So what is a stochastic inverse problem? Well, the inverse problem is the inverse of a direct problem. So direct problem, you have some parameters you want to go to be able to do the model, the forward one, from parameter to response. The inverse problem is the opposite. You've observed something, you have observed an outcome, and you would like to infer what was behind it, what was the cause, what were the parameters behind it, but it's much harder to do than the direct one. Because these kind of problems tend to be ill-posed, you might have observation noise, you might have a system that is not invertible, and it's just not easy going from response to parameter. It's much more complex, the relationship in the inverse sense than in the direct sense. So something that is done a lot is to use a probabilistic approach. Instead of saying, oh, I'm not able to solve the math to go directly from this to that, I'm not able to do anything analytically, what I'm able to do is that I can summarize all my beliefs or my prior knowledge on the X in the form of a prior by saying, oh, this is the X I'm expecting to see. And then you can use Bayes' theorem to account for your data and to say, well, knowing what I have observed, here is how I update my belief and my knowledge about these parameters, and this is what I'm trying to find. So this is a way to tackle the fact that it is not well posed, but the issue is that you still have a likelihood term, and this term tends to be quite hard to get. Because if you're dealing with complex problems, then you don't have a closed form for the likelihood, or maybe it's really expensive, you cannot deal with it nicely. So what you can do is say that I cannot do it analytically speaking, but I'm able to reproduce other experiments. I'm able to rerun experiments, either computer simulations or just do it in practice in the lab or something. And so I will use simulations to replace this thing where the likelihood is not available with simulation. And that's the whole framework of approximate Bayesian computation, is saying what I will do is that I will use my friends that are experts in their fields to ask them to make me new experiments, and I will compare the outputs. And if my new simulation is close to the one that I had observed, then the output is likely to be a good one. And then if it's far away from what I observed, then it's a bad input that I put in it. And that's the whole idea. You just take some notion of what it is to be similar, you just keep the one that are interesting and you solve the other. So for instance, if I were to run 5 new simulations for 5 x's, and I compute a distance that makes sense for my problem, here I would reject 3 of them. I would say, oh, this is the experiment for x4 is way too different from what I had for x1, for my reference. So I cannot keep x4, it's not plausible. But x2 looks quite similar to what I had. Maybe it's something that looks like x2. And you get this ABC posterior that is actually a histogram. The issue is that this is quite expensive in terms of computation you need to do. Because if you want your approximation of the posterior to be good, you need to be really picky about what it means to be close enough to your observation. And then you need to make a lot of experiments because you're going to reject most of them because they are going to be too far away from it. So you want to be able to do something to accelerate it. And the idea that was already around for Gaussian process ABC, but that we have revisited with spatial logistic Gaussian process, is just to say, what I can do is I can model the distribution of these misfits of these points that are accepted or rejected, and then I just need to take the CDF basically to know what is the probability to be below the point.
I have a silly question about computational cost of ABC.
Yeah.
In your example, is it huge? How costly will it be on your example?
So it depends on how much it costs to run an experiment. So practitioners, when they do ABC, they tend to set a threshold that is like, I will give myself a budget of, I don't know, 100,000 evaluation, and I will keep the 100 best. So they don't really put the threshold, they do quantile wise. And it depends on experience. So what we did for the one I'm about to show, I had a computer that's actually computed everything ahead. So I had the data set of dissimilarities, and that's it. The other test case that was interesting to us was a cosmological one, and then each run took several hours on the supercomputer. So it's really something like every time you make a simulation, it can take up to a few hours, and then you reject it because you did not run it for X that was interesting for you. Mm-hmm. So that was a bit the issue. And the other issue with ABC that you need to compute to make the simulation to something that is either an X that comes from the prior or to some distribution related to the prior. You cannot take any X you like by saying, oh, I will focus on just this region that is interesting because it's not rejected, because otherwise you get overconfident and you pick your posterior too much. So that's something also that is annoying, that when you run ABC in practice, you tend to do a lot of simulations that you know are going to be rejected. And being able to have a model over the similarities and know which one are going to be rejected and which one are not, then it enables you to keep the information from all the data points, including the one rejected. Because if I have a really high distance here, I can also learn this structure in my meta-modeling, and then I can reuse it later. So the idea for GPABC was just to model the misfits with a GP or log GP. And what we said that we're going to model the misfit distribution with a GP. So we're saying we will replace this term of misfits being smaller than a threshold, knowing it should be an X here, it's a typo. And knowing this with a cell GP, and then I can plug my prior and get a posterior. So what is interesting about this is that it starts working in low data regime. So even when I have a few computations and I would reject most of them, I'm still able to learn some structures because I'm learning the whole distribution of misfits. I don't need to have some assumption on misfits likelihood of misfit shape because, for instance, when you do GPABC, you assume that you have the main dependency that is in the mean and that you don't have some artifacts close to the tail or multimodalities. If you have these, it can be tricky because you will miss them because you will model the mean and maybe you will miss some probability mass close to smaller values. And you can use this on any data set. You don't need to have a data set that was generated according to a given structure. So you can also use it to check later, or you can just run offline. And because we have consistency for SLGP, we can also extend it to SLGP ABC. So it's also quite nice to know that you will get the right posterior. So we had an application with a co-author that is Guillaume Pirot, that is currently at the University of Western Australia, that comes from hydrogeology. So we have an aquifer that is basically an underground river. We know that a contaminant is released in it at a depth. We don't know which depth. We know it's going to flow through the aquifer. And we know that we are going to observe it at some boreholes. We are observing the concentration of contaminant over time. But we don't know what's the structure of the aquifer behind it. We don't really know what it's like, so we cannot predict like, oh, if I release it here, it will arrive exactly here at this time, because I have this uncertainty. So we would like to be able to find the source without knowing the structure, and we're not really interested in knowing the structure, we just want to find the source here. So the structure is a cause of uncertainty. So if I release my contaminant, I don't have access to the map on the left, but I'm still showing it to you. You can have a small animation that I'm releasing contaminant is going to spread through the aquifer that is here, and you will see here what we observe at the boreholes over time. So here, see it spread, it starts arriving at my sensors, then it arrives, and then all the contaminant is gone. It's good. And we end up having just this contaminant plum. And we like to say, well, what was the source behind it? So first, just by looking at it, you can say the source is about 5 meters deep because everything arrived at 5 meters deep. But maybe if you have some high channel here, it could have arrived from higher up or something like that. So you're not sure. So what we do is that my colleague, is really good in hydrogeology, he can make me new simulation. He can tell me, well, maybe this is what the aquifer looks like, and then if I put the source close to 5 meters, you get this contaminant plum, and you can compare it to the one you have, and you can get a low misfit. Or maybe this is what the aquifer looks like, and if I take another source, we get this plum, you can compare it, the misfit is higher. Or maybe this is what, and so it can make me a new simulation accounting for the uncertainty. We can compute the misfit, and in the end, it puts all this expert knowledge in the simulation, and it just gives me the misfits. So this is not what I actually want to work with exactly, in the sense that I don't want to have to do 10,000 simulations before I have some knowledge of what's happening. But it was still interesting to look at it because that was one of the things motivated, the fact that we want to tackle multimodality or versus unimodality and changes of shapes. So this is why it was important to us to have this flexible model. So we just applied this self-GPABC framework by starting with a much lower number of points. So if I take just 10 simulations and I put my threshold, I selected it such that 1% of all simulation would be accepted if I use this threshold, just to see that it's a bit challenging for the ABC and we can start doing some things. So here, none of the 10 simulation will be kept because none of them are under the threshold for the misfits. And on the bottom panel, you see you have the prior that is just uniform. And I also put a blue diamond to show you the actual source, so we can see if the inference is trying to find the real source. So right now, standard ABC tells me nothing. If I learn these distributions of the misfit indexed by the source depth, then I would be able to have the SLGP ABC posterior. I have a lot of variability. It's not so easy to see from the posterior draws if I'm learning something or not, but if I have the posterior mean, I'm starting to be maybe thinking that it might, with a lot of variability, be in the middle. It's because you have a slight V shape and this low value here that is saying, oh, maybe you have some structure, but we're not sure. If I add more points, 100 simulations, first I see I have a strong spatial structure, and I would keep just 2 points for my SLGP ABC. So my SLGP ABC posterior is the histogram with 2 points in it. But because the spatial structure is used, I have these, both the draws and the posterior mean are quite more confident that it's in the middle. And then if I have even more data, so for 500 simulations, I would keep only 8 points with standard ABC, but I'm already able to have a really good approximation and really confident where my posterior is for the SLGP ABC one. So it's really able to help draw the knowledge from the data and the structure from the data by using all the data that we would have discarded in standard ABC approach. So one thing that we used for that is that not only we can make the inference like this, but we can also use the fact that we have some uncertainty on the inference to try to guide data acquisition. And that's something that we're currently working on. And so that was mostly what I wanted to show you. Here are the references. I hope you enjoy them. We've used it, so we've shown this idea of doing the inversion with the model. We also try to use it to model the output of the system for Bayesian optimization and then get some sequential acquisition strategies. And I have a vignette that is also doing inversion. Like I'm learning temperature distribution in Switzerland and I'm saying, oh, if I'm freezing and it's -15, where am I? And it's able to say, oh, you're in the mountains. So I'm really happy about it because it makes sense. And so that was mostly what I wanted to show. So I introduced you to this class of model that is the Spatial Logistic Gaussian Process that is quite flexible. It's a non-parametric modeling. It does not require distributional assumptions. It comes at maybe higher computational cost, so it's a bit heavier because you need to run some estimations on MCMC. I gave you a peek at the theoretical properties we have and how we derive them and why it makes things work in the background with spatial regularity. I showed you a bit what we are starting to do and planning to continue doing for the SLGP ABC framework for inversion and this hydrogeological application. And currently what I'm working on with respect to that is that there is the package in R that is submitted and should be released at some point, the implementation paper that is in the proofreading part for me. I want to work more on this SLGP ABC. I also want to work more on, as you said, evaluating, like having a methodical framework to evaluate whether things are good. That will be especially relevant for the SLGP ABC, because then how do you evaluate that your SLGP ABC posterior is good compared to your ABC posterior? That's something that really requires some methodical approaches. And then I want to do some benchmarks to compare to some competitors, to compare to what's happening with your data. Because we can also agree that GP ABC would have been amazing for this data set because the data was actually quite behaved. The case study was so nice that it was really easy to draw some knowledge, but some other application might be more challenging with more stronger impact of data. And I also want to try other data sets and see what happens, trying to scale it. Thank you.
Yes, this question, did you try to apply it to SPDEs? Instead of going to real data set, just go to like some real analytic models, like stochastic heat equation or.
No, I do not.
But do you think that this would work? I mean, at least you would be able to get some good analytic results if you do it. If you start from models, maybe
yeah.
you can. Yeah.
So I do not consider it until today, so I have to think a bit more about it. I think it's quite a promising idea. I never thought about it. Yep.
Your inverse problems.
Yeah.
Can't you just use directly the GP model as an approximation of the likelihood?
Yeah, so this is actually what inspired for the SL-GPABC avenues, is that GPABC is already speeding up quite a bit. And as I mentioned at the end of this application, indeed for this one, GPABC would have been amazing as well, because you have such a strong V shape that you don't care about the fact that it's bimodal here and unimodal here. You still capture everything with the mean. There were a few things that were interesting, that were still driving these developments. Is at first we would want to have some guarantee that these models we use to spinning up inference are not giving you, so the colleagues from cosmology, they really wanted to be sure that they were not overconfident. And so they did not want to use, for instance, GPABC and take the risk of being too confident in the posterior, because they really want to have the right uncertainty. And so it was, at least one of the motivation was like, if you have a model that is more flexible, you're less likely to, because of model misspecification, be overconfident or assess wrongly the confidence you have in your results, or the variability of your results. That was something. And also because you can, this was one application, but you can have other shapes or other application, and then it's not guaranteed that for the other one, you're going to have such a strong structure. Actually, even in other geological application, you have things that are much flatter, and then a SL-GPABC is still able to learn things. GPABC was struggling a bit more because it was not understanding bimodal structures, and so it was putting everything a bit higher up. I think the way to address this would be to have a big benchmark. I think a way to compare the performances that is really principled, plus doing the benchmarks to see when one is suitable and what is not. But overall, it just depends on your model's structure, and you cannot know that beforehand, most likely. Like, you cannot know in advance, oh, my model is going to be my bimodal here and unimodal here, so I can do that. Because otherwise, you would not have such a big issue with doing the inversion in the first time if you had this amount of structural knowledge, I think. So it can be quite case dependent.
Shortly, and so for the housing example,
Yeah.
I mean, do you have something? I mean, I try to understand this a bit, but I mean, you have, I mean, for sort of creating your co-creating. So if your data of your housing example would be someone that walked around and said, okay, I started, whatever, 10 houses, this age, this value, and the sum is 1 million. And then I did another one. So you have this sort of linear averages like this.
Yeah.
Is there a way to make this sort of integrate in the same way that you can easily, when you do sort of creating type of example, you have linear averages, you can easily do co-creating, update your estimate, or do you run into some sort of issues in doing that?
So I guess, first, I guess that the housing data set is so well used and well known that people have tried doing that, I guess, because a lot of, it's like, if you do images, you show everything on the MNIST, and if you do regression, you show in data set like this, because they are, well, I saw it in school already. For the co-creating,
Yeah, so I mean, I'm not saying that you would do co-creating on this data. I'm just saying, in the case where you have linear averages as data,
Yeah.
so linear problem, could there be an equivalent that would allow you to work with your framework to deal with that case? Because now you have samples at local locations.
I have some summary statistics of samples at some locations. I don't know directly, in the sense that, for instance, the median is not a linear output. So I mean, anyway, we don't have access to what's behind the median value. We don't know how many houses. We don't have the data behind it. So I guess we cannot really. What I understand, you're saying that I could take the underlying values behind this median value and then push everything through the statistics, or
Maybe my
okay,
question is not-
maybe I misunderstood the
we can
question.
start
Really nice talk.
Thanks.
I want to ask about the basic expansion bit. I mean, I've got questions about the ABC bit, but maybe offline. But the basic expansion. So presumably your cost scales the number of basis functions if you're doing MCMC. There's a penalty you pay for having more. Is it worth thinking about optimal choices of basis functions here? So like a KL basis or something like that, rather than kind of random Fourier features. Is there any benefit to that here?
So first we did some analysis of what happens if you know the underlying, like, you know the ground truth, you do new simulation and all that. The first thing we see is that you have some compromise between sample size and number of basis function, of course. So at first the performances are the same no matter the number of basis function, and when you get more data, you tend to see a difference in performances. So for instance, here, if I have some dissimilarity that is just taking Hellinger distance and integrating to average over the x's, and I take, so it's cropped. I take different number of basis functions and I increase the sample size from one thing. You have, at the beginning, you have really similar performances. They cannot really distinguish between the number of basis function, and then when you acquire more data, you start to see that the lower order models, so the one with less basis function, are limited and they are in a misspecified result, and you can actually understand what they are trying to model because there are papers about it. So you have some compromise, like depending on the number of data you have, you should take more or less functions. It's a bit hard to find optimal number of basis functions because you would need to have a metric that evaluates what's good, what's optimal, and here we can because we have the ground truth, the data generating process, but in practice you only have the data points, so you need to have something like that. I would tend to say, I would say that in doubt, just take more because it's not, it's making it a bit slower, but it's still, this log concave result still makes it fairly okay. So even if you increase the dimension, maybe if you take quite as much function, then it's not that bad.
So I'm not particularly asking about the number of basis functions, but the choice of particular basis functions. So you know, say you didn't have the exponential there, you know that the optimal choice of basis, like a Calhoun and Lerve expansion, or whether you can find, I don't know, it probably wouldn't be optimal in your model, but whether there is a benefit from thinking about the optimal choice.
I don't. So Calhoun Lerve is just optimal because it's normal with respect to but then we don't really need we don't really benefit from this orthonormality.
Okay.
So I don't see a big difference in taking this kind of optimal function because we are not in the L2 context of kernel OF, so we don't really care in the sense that the exponential is mixing everything anyway. Maybe there is a good family because of that. I did not look at it, but actually we started thinking of this because kernel Lerve, and then we realized we don't need to evaluate or approximate basis function because it's just more costly, and we can just say, oh, we take this kind of shape. And so instead of going from the kernel that we select and then trying to find the kernel Lerve expansion, went from kernel to Coué features, and it also gave something. So.
Just to follow up, I guess the theory would give you a low bound on the number of P you need to take, because obviously if you take too low, you wouldn't get posterior consistency, you wouldn't get the right approximation. Yeah, because, well, if you don't take the good amount of P, what you're actually doing is that you're taking a GP that's a RKHA that is too small, basically, does not have enough functions. And what you are concentrating around, because you've seen that it was concentrating, you're concentrating around the element that minimizes the Kullback-Leibler divergence with respect to the true one. That's also, there is a paper, I think it's 2013 from Van der Waart to study misspecification in this setting for Gaussian processes, and it's really easy to adapt it to understand what's happening when you're misspecified. So yeah, that's what's happening.
All right.
thanks to all and the speakers and discussants. We continue.